What are vector components? How do you calculate the components of a vector? Is there an easy way to calculate vector components? These are all great questions and will be answered today on Physics with Joe, where I'm going to be discussing everything you ever wanted to know about vector components, but were afraid to ask. So let's not waste any time. Let's jump right into it. Before I go into what a vector component is, let me remind you that the way we represent vectors visually is by using an arrow. The length of the arrow is proportional to the magnitude of the vector, and the direction the arrow is pointing is in the same direction that the vector points. Let's assume these are force vectors. So right now C has a magnitude of 10 newtons and it's pointing straight down at an angle of 270 degrees or negative 90 degrees. If instead C had a magnitude of 20 newtons, I would draw that arrow twice as long as when it was 10 Newton force. If instead of pointing straight down, this force vector pointed to the right, then I would draw the arrow pointing to the right. At its most basic, a component of a vector is really just how much of that vector points along a given axis. Generally, we're looking at the x and y components of a vector, which is how much of that vector points along the x-axis and how much of that vector points along the y-axis. If you take a look at vector A here, vector A, again, we're going to assume it's a force vector, so the units are newtons. Vector A has a magnitude of 22.4 newtons, has an angle of 26.6 degrees. The x component of vector A is represented by this horizontal arrow. The length of that arrow would be proportional to the x component of vector A. Since it points to the right, we'll get to this in a second, but the x component is positive. The y component of vector A is represented by this arrow pointing straight up. Again, the length of that arrow would be proportional to the y component of vector A. Since it's pointing straight up, the y component is positive. And in fact, let's just take a look at vectors only pointing in one direction, either horizontal or vertical, so we can look at the signs. So let's get rid of vector A. So vector C has a magnitude of 10 newtons. If vector C, again, I'm going to draw it connected to the axis, to the origin, but that's not important. All that matters is what direction it's pointing and how long the vector is. If I have a vector that only points to the right, then it only has an x component because there is no part of that vector pointing vertically. And since it points to the right, the x component is positive. In one dimension, we indicate direction with a plus or minus sign. In the x direction, plus generally means to the right, minus means to the left. In the y direction, vertically, positive means straight up, negative means straight down. So if I have a 10 Newton force pointing only to the right, the x component is 10 newtons, there is no y component. If instead this vector was pointing to the left, now my x component is negative 10 newtons because it's pointing to the left, and that minus sign is indicating a direction. It's indicating a 10 Newton force pointing exactly to the left. If instead this was pointing straight up, now I do not have an x component because there is no part of that vector that's pointing horizontally. The y component is 10 newtons, no x component. On the other hand, if this vector pointed straight down, again, I have no x component because no part of this vector is pointing horizontally, but it's pointing straight down, so my y component is negative. I have a negative 10 newtons for my y component. 10 newtons is the magnitude, and the minus sign is indicating that it points straight down. If a vector is not only pointing horizontally or only pointing vertically but at an angle, then that vector is going to have both an x and a y component. Now visually, the easiest way I think to look at what are the x and y components is by starting at the tail of the vector and drawing a right triangle where the arrow is the hypotenuse. The x component is how much of this vector is pointing horizontally. The y component is how much of this vector is pointing vertically. Before I go into actually calculating these vectors using trigonometry or my patent-pending Southern California approach, it's good to know whether the x and y components should be positive or negative depending upon the angle of the vector. Let's just draw this vector connected to the origin. Again, remember, it doesn't really matter where the vector is drawn, but any angle between 0 and 90 degrees relative to the positive x-axis, so something in the first quadrant, is going to have a positive x component, a positive y component. You can see the x component's always going to be pointing to the right, the y component's always going to be pointing straight up, and it doesn't matter what the magnitude or angle is as long as it's between 0 and 90 degrees and it's in the first quadrant. If instead the vector is in the second quadrant, so an angle between 90 and 180 degrees relative to the positive x-axis, now you can see that the x component is pointing to the left, so I have a negative x component. The y component points straight up, so I have a positive y component. Again, it doesn't matter what the angle is. If it's between 0 and 90 degrees, between 90 and 180, I'm going to have a negative x component, positive y component. In the third quadrant, so any angle between 180 and 270 relative to the positive x-axis, the x component is going to be negative, the y component is going to be negative. You can see that any angle in the third quadrant, I'm going to have that particular vector pointing to the left horizontally, straight down vertically, so it's going to have an x component that's negative, a y component that's negative. And last but not least, if the angle is in the fourth quadrant, so any vector that has an angle between 270 and 360 relative to the positive x-axis, you can see that the x component is pointing to the right, the y component is pointing straight down. So in the fourth quadrant, you're going to have a positive x component and a negative y component. Let's spend a minute talking about vector notation. How do you notate the difference between a vector and the magnitude of the vector? Now, this is going to depend upon the textbook that you use. Most textbooks generally indicate vectors one of two ways. They take the symbol for the quantity, like F for force, V for velocity, A for acceleration, and they either bold that symbol or they put the symbol with a little arrow over top. So for example, if I wanted to indicate a velocity vector, here I can't really bold it, but I would draw V with a little arrow over top. And if I wanted to indicate an acceleration vector, I would draw A with an arrow over top. Now, it does not matter the direction that the vector points. Whenever you're indicating it by using notation, you always draw the arrow pointing to the right. On the other hand, if I want to indicate the magnitude of a vector, most textbooks also generally use one of two ways. They take the symbol and they italicize the symbol, or they put the symbol with the arrow over top, like for velocity, inside an absolute value sign. Now, it's not really the absolute value, but it is indicating the magnitude of the vector. So up here, V and A with little arrows over top, this is indicating the velocity and acceleration vectors themselves. And if I have these vector symbols inside an absolute value sign, then this is the magnitude of the vectors. This may seem like a subtle point, but it is important because there's some equations that are true as vector equations, but not as magnitude equations. For example, let's take a look at this vector A. A is pointing in the first quadrant, and it's got a positive x component, which is pointing to the right, and a positive y component, which is pointing straight up. If you remember the tail to tip method, you can see that if I take the x component and I add the y component to it, I do get my original vector here. So here's my a vector, here's my x component, here's my y component. I can say with all certainty that the x component of A plus the y component of A equals vector A itself. This is a vector equation. What I cannot say is that the magnitude of the x component plus the magnitude of the y component will give me the magnitude of the vector itself. So this is not true, and in fact, it will never be true. I can never say that the magnitude of the x component of a vector plus the magnitude of the y component of a vector will equal the magnitude of the vector itself. We'll see in a second the way the magnitudes are related is through Pythagorean theorem. Just as a quick little example, you probably have seen a 3, 4, 5 triangle at some point in your mathematical studies. It's a popular right triangle. I cannot say that 3 plus 4 equals 5. That's not the way they're related. However, they are related through Pythagorean theorem. I can say that 3 squared plus 4 squared equals 5 squared. Since we use trigonometry to calculate the x and y components of a vector, I thought it prudent to spend a couple minutes reviewing all the trigonometry you need to know in order to be a vector ninja. And the good news is there's only really 2 things you need to know from trigonometry to work with vectors. 1, Pythagorean theorem. 2, SOCA. Both of these apply to right triangles, which, as a reminder, is any triangle where one of the angles is 90 degrees. Pythagorean theorem relates the lengths of the sides of the right triangle to the length of the hypotenuse. And it simply says a squared plus b squared equals c squared. Where a and b are the length of the 2 sides, c is the length of the hypotenuse. And then SOCA, hopefully you remember, is an acronym. It stands for the sine of an angle equals the opposite side divided by the hypotenuse. The cosine of an angle is the adjacent side divided by the hypotenuse. Tangent of an angle is the opposite side divided by the adjacent side. And that really is all you need to know. As a preview, we're going to use Pythagorean theorem 2 different ways when dealing with vectors. 1, we can use it to double check whether the magnitudes of our x and y components are correct. If the x component of a vector squared plus its y component squared does not equal the magnitude squared, we know we've made a mistake. Second way is if we already have the x and y components of a vector and we want the magnitude of the vector, we can use Pythagorean theorem to calculate that. We'll also use SOCA 2 different ways when dealing with vectors. 1, given the magnitude and direction of a vector, we can use either the sine or the cosine to calculate the x or y components. And then 2, if we already have the x and y components of a vector and we want the angle or direction of the vector, we can use inverse tangent to calculate that. So let's actually go and start calculating some vector components. Let's look at an example where we calculate the x and y components of 2 different force vectors. I'll go through this step by step, and then when I'm done, I'll show you an easy way I like to call my Southern California approach, SOCA. That'll make calculating x and y components very easy for you. First thing I like to do is 1, think about whether the x and y components of a particular vector should be positive or negative. And then 2, whether I expect the magnitude of the x component to be bigger or smaller than the magnitude of the y component. So this problem is, vectors A and B are 2 force vectors. The magnitude of vector A is 75 newtons, and the magnitude of vector B is 50 newtons. What are the x and y components of each vector? So here we have vector A, and the x component of A points to the left, so I know it's going to be negative. The y component of A points straight up. And you can see the x component is bigger than the y component in terms of the magnitude, so I expect the magnitude to be bigger. For the B, the y component of B points straight up, so it'll be positive. The x component points to the right, so it'll be positive also. Now what you're doing to calculate the magnitudes of the x and y components is really just using SOCA, and it's really just using sine and cosine. So remembering that sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, then all you're really doing is taking the angle that you're giving and then looking at sine and cosine. So let's look at, here's my triangle for A. I've got my x component, I've got my y component, here's my magnitude, and my angle is 30 degrees. Let's just start with sine. I know the sine of 30 degrees equals the opposite side, which in this case is my y component, divided by my hypotenuse, which is the magnitude of 75 newtons. If you solve for the y component, what you will get is it's 75 newtons times the sine of 30 degrees. And this will give us the magnitude of the y component, which is 37.5 newtons. Let's look at the magnitude of the x component. Well, we're going to start with cosine. I know the cosine of an angle equals the adjacent side divided by the hypotenuse. So in this case, the adjacent side is the x component divided by the hypotenuse, which is the magnitude of 75 newtons. So my x component is the magnitude, 75 newtons, times the cosine of 30 degrees, which is 65.0 newtons. However, this vector is pointing to the left. So in terms of the x component of A, I would write that as a negative 65 newtons because it is pointing to the left. So the magnitude is 65 newtons, the direction is to the left. The y component is 37.5 newtons. Now we can do a quick check because the magnitude of the x component squared plus the magnitude of the y component squared should equal the magnitude of the vector squared. So does 65.0 newtons squared plus 37.5 newtons squared, does that equal 75 newtons squared? And in this case, it does within a rounding error. If it didn't, that would indicate that you made a mistake. Let's look at vector B. In this case, we got our x component. It's right here. Our y component, our magnitude is 50 newtons, and our angle is 35 degrees. Again, we can start with sine. So the sine of this 35 degree angle is going to be opposite side divided by the hypotenuse. So it's going to be the x component divided by, 50.0 newtons. So my x component is my magnitude, 50.0 newtons, times the sine of 35 degrees. And that ends up being 28.7 newtons. And then my y component I can get by looking at cosine. Cosine of 35 degrees equals my adjacent side divided by my hypotenuse. So it's going to be my y component divided by my hypotenuse, which is the magnitude, 50 newtons. So my y component equals 50 newtons times the cosine of 35 degrees, which is 41.0 newtons. They're both positive because the x component points to the right, the y component points straight up. Now, the more you do these, the more you'll see a pattern. The x or y components is always plus or minus the magnitude of the vector times either the sine or cosine of the angle. And the easiest way to know whether it's sine or cosine, just from SOCA, sine is always going to be related to the opposite side. Cosine is always going to be related to the adjacent side. So what I kind of call my Southern California approach is the following. The x or y components of any vector is going to be equal to plus or minus the magnitude of the vector times either the sine or cosine of the angle. How do you know which one you use? Well, sine is always going to go with the opposite side. Cosine is always going to go with the adjacent side. If you know the x or y component's going to be negative, you have to put that minus sign in. And once you get used to this, it's really, really, really quick. So let me just do a quick example. Let's say that you have a force vector. We'll call it F. The magnitude of this force vector is 100 newtons. And you're told this is a 28-degree angle. My y component points straight down. My x component points to the left. Here's my 28-degree angle. My magnitude is 100 newtons. Here's my x component. Here's my y component. Now, you could go through and do the exact same procedure I did before, where you're starting with either the sine or cosine. But really, you don't need to do that extra step. At the angle and see whether the x or y components are the opposite side or the adjacent side. And then you know exactly which sine or cosine you're going to need to use. So here, my x component. One x component is pointing to the left, so I know it's going to have to be negative. So I could just say fx, my x component, is negative. The magnitude, 100 newtons, times, in this case, since it's the opposite side, I'm going to use the sine of 28 degrees. And then my y component, again, since it's pointing down, I know it's going to have to be negative, so I'm going to put in a minus sign. The magnitude times either sine or cosine. In this case, the y component is the adjacent side to this 28-degree angle, so I'm going to use cosine. And then you can go and calculate which each of these are. So we've got 100 newtons times sine of 28 degrees, 46.9. So I've got 46.9 newtons. And 100 newtons times cosine of 28. It's 88.3. 88.3. And keeping in mind both of these are pointing in the negative direction, so I have to have a minus sign for the x and y components. And again, that minus sign is indicating a direction. So the x component has a magnitude of 46.9 newtons, and it points to the left. The y component has a magnitude of 88.3 newtons, and it points straight down. Let's quickly review the Southern California approach to calculating vector components and do two last examples. So anytime you're calculating the x or y components of a vector, it's always plus or minus the magnitude of the vector times either sine or cosine of the angle. The plus or minus indicates direction. Along the x-axis, if the x component points to the right, it's positive. If it points to the left, it's negative. Along the y-axis, if the y component points straight up, it's positive. If it points straight down, it's negative. And then in terms of sine or cosine of the angle, you determine which one by either being the opposite side or the adjacent side. SOCA! SOCA! Sine is always associated with the opposite side. Cosine is always associated with the adjacent side. Let's look at two quick examples. F1 is a 62.5 Newton force. It is 25 degrees above the negative x-axis. F2, a 125 Newton force. It is 35 degrees to the right of the positive y-axis. And what we want to know is, what are the x and y components of each force? Well, F1, I know the x component points to the left, so it's going to be negative. It is the adjacent side to the 25-degree angle, so I know I'm going to use cosine. So the x component of F1 is given by negative 62.5 newtons times the cosine of 25 degrees. The y component points straight up, so I know it's going to be positive. It is the opposite side to the 25-degree angle, so I know I'm going to use sine. The y component of F1 is 62.5 newtons times the sine of 25 degrees. And you can see the values there if you want. For F2, the y component of F2 points straight up, so I know it's going to be positive. The x component of F2 points to the right, so I know it's also going to be positive. The y component is the adjacent side to the 35-degree angle, so I'm going to use cosine when calculating the y component in this case. The x component is the opposite side to the 35-degree angle, so I know I'm going to be using sine. So for F2, the x component is 125 newtons times the sine of 35 degrees, and the y component, 125 newtons times the cosine of 35 degrees. And that's really all there is to it. The more you do this, the easier it'll be. And once you start getting to Newton's laws and free body diagrams, this is such a powerful and useful way of calculating components of forces. If it's the opposite side, you use sine. If it's the adjacent side, you use cosine. It's always plus or minus the magnitude of the vector times either sine or cosine. Well, that's really it. My name is Dr. Joe McCullough. Thank you so much for joining me, and I hope to see you next time. Until then, keep physicking. Until then, keep physicing. Until then, I'll see you next time.